In this fork are also, you can use the word dining philosopher. There is a kind of problem is occur like deadlock problem. In this problem, every philosopher need a fork, but if they access or they follow the kind of instructions, then still one person is remaining for acquire the fork. In the starvation condition, allow them only 2% to access the forks and others should remain in waiting, and after releasing them they are allowed to access in that situation. Number of philosophers is there 5, and I philosopher number is 0 to 4 is initialized. Now number of thinking philosopher is thinking called the function, and fork I accessing the number of forks, and allow only 2 persons for accessing the fork. They are allow them to eat, and then again allow after releasing them put the right fork back on the table and left fork back on the table. This sequence is followed. A known solution to the dynamic philosopher problem. Dynamic philosopher come into the next situation where number of philosopher representing as 5, number of I left neighbor is n, which is calculating with the modulus, and this steps are need to follow for completion their problem. But in the same manner there is a kind of problem occur like mutual exclusion, and you can say acquiring problem and forks accessing at the same time. Solution to dynamic philosopher problem is allow 2 of them for accessing and another should wait. A barber shop consists of a waiting. This is another problem that can you say the sleeping barber problem. A barber shop consists of a waiting room with chairs and the barber room containing the barber chair. If there are no customer to be served, the barber goes to sleep. If a customer enters the barber shop and all chairs are occupied, then the customer leaves the shop. If the barber is busy but chairs are available, then the customer sit in one of the free chair. If the barber is asleep, the customer wake up the barber. In both cases, barber we want to make busy and we want to utilize his efforts in this system. If all the chairs empty, then and barber can sleep, and if all the chairs are busy and the customer is coming, then he leave out from there. So the sleeping barber, if number of chairs are available, we have to apply the condition for exiting the consumer when the all chairs are full and barber is busy. And another case when the condition is satisfied and consumer is satisfied after their job, then he can leave from that shop. Then the next topic is locks. In this, locks are another synchronization mechanism. A lock has got 2 atomic operations similar to semaphore to provide mutual exclusion. These 2 operations are acquire and release. These operations should be followed for acquiring the lock or for storing the data. After storing the data, we need to acquire lock, and after locking that particular data or that particular task, if we want to access that, then we have to again acquire lock and then release that particular lock after acquiring for storing and accessing the data. These are the situation: lock acquire, then enter into the critical section, then lock release. This is the sequence is followed for accessing the data by the number of processes. The difference between a lock and a semaphore is that a lock is released only by the process that have acquired it earlier. Which one acquired the resource or lock earlier have to release that particular lock at first. Next is monitors and condition variables. Monitors and condition variables problem, or in this topic A concurrent programming, a monetary synchronization construct that allow thread to have both mutual exclusion and the ability to wait for a certain condition to become true. In this case, number of processes are there for execution and for completion their task. If number of processes are executing their task, then the another process have to wait, and they are able to wait or allow them to wait for accessing the data, for accessing the resource or system. In that case, we have two conditions. A condition variable is a basically container of a thread that are waiting on a certain condition. Monitor provide a mechanism for thread to temporarily give up exclusive access in order to wait for some condition to be met before regaining exclusive access and resuming their task is required. If we want to access the data, then we require the exclusive access. If we want to release that particular system or particular data, we have to resuming allow to another process to enter the system. And the next topic is deadlock. In this, we have some conditions as like mutual exclusion condition, hold and wait condition, no primitive condition, and circular wait condition. These all conditions are for the situation where deadlock get occur and deadlock is existing into the system. If we want to prevent our system to enter the deadlock situation, we have to prevent our system to enter any one of these conditions, which are the characteristic of deadlock. Now come to the topic types of resources. Preemptible resources. These resources can be taken away from the process with no will effect. Memory is an example of a preemptible resources. And the next is non-preemptible resources. This resource cannot be taken away from the process without causing will effect. For example, CD resources are not preemptible at an arbitrary moment. Preemptible resources are resources which are acquired by a system and exiting system on the requirement, and non-preemptible resources are the resources which hold by a process but not getting released that particular resource after completion their task, or continuous retaining that kind of resource for a longer term. This may cause the problem of deadlock. In deadlock, there is a permanent blocking of a set of processes that either compete for system resource or communicating with each other. Deadlock is a situation when we have the number of processes in execution state and every process requesting for another process by retaining the existing resource, and every process getting busy in execution their task, but they are requesting for that process which is held by another process and not going to release the existing resource which is held by them. So there is every process is waiting for another process, which is every process retaining the resource which is held by another process. No efficient solution is there for preventing that situation. Involve conflicting needs for resources by two or more processes. So the conditions are: first, mutual exclusion. In this situation, only one process may use a resource at a time. The resources involved are non-shareable. The next is hold and wait. In this, a process requests all of its required resources at one time. And the next condition is no permission. If a process holding certain resource is defined or denied a further request, that process must release its original resource. If a process requests a resource that is currently held by another process, the operating system may preempt the second process and require it to release its resource. The next condition is circular wait, prevented by defining a linear ordering of resource types. In this problem, a resource is held by a single process, but it is requesting for another resource which is held by another process, and this thing is happening between more than 2 and more than n number of processes. So the circular waiting condition is occurred at the time. So we have to manage kind of problems, like example is there traffic deadlock. In that case we have the number of ways, and you can say there is the 4-way east, west, north, south, and the traffic is coming from all directions at the same time. So in that situation the traffic is get choked and nobody is able to move and go further. That kind of situation we can say the deadlock situation. In the other way, the deadlock can be possible if the number of vehicles entering into the particular way or entering into the particular deadlock condition is not allowing anybody to go out or exit from that way, and they are continuous entering into the queue and not going to release the way to allow any other traffic from the other direction. These are the illustrations of deadlock. Now come to traffic deadlock. Mutual exclusion condition applies since only one vehicle can be on a section of the street at a time. And the next is hold and wait condition applies since each vehicle is occupying a section of the street and waiting to move on to the next section of the street. The next one, no primitive condition applies since a section of the street that is occupied by a vehicle cannot be taken away from it. And the next is circular wait condition, which is very much popular. In deadlock condition applies since each vehicle is waiting for the next vehicle to move, that is each vehicle in the traffic is waiting for a section of the street held by the next vehicle in the traffic. This condition, you can say the characteristic or you can say the causes of deadlock. If we are able and if we able to remove any kind of this problem, so we are able to remove the deadlock condition. And this is also the example of deadlock where the number of progresses are there, like get B, get A are the request and required by the resources, and if anybody is going to release, and there is also mentioned the number of release progresses and processes. If every process requesting for another resource and not going to release existing resource which is held by it, so the deadlock condition possibly will occur in that situation. If we want to deadlock is not occurred into the system or into that scenario, so we have to make some space, we have to make some situation where any one of these condition will not occur. If we able to remove any one condition from the given conditions, then we are able to remove the deadlock condition from the system. So next topic is resource allocation graph. Resource allocation graph is a graph in which deadlock can be described through a resource allocation or through a diagrammatic form by using number of processes for represent as P1, P2, and for representing resources we are using R1, R2. As in such situation, a directed edge from a process to a resource implies that Pi has requested for Rj resources. A directed edge from a resource to process Rj implies Pi implies that Rj has been allocated by Pi, means Rj resource allocated by or allocated to Pi. If Pi implies Rj, means process Pi requesting for Rj resource. If the graph has no cycle, deadlock cannot exist. If the graph has a cycle, deadlock may exist into the system. So this is the graphical notation of resource allocation graph. In the first notation, there is the number of processes are there as like P1, P2 and P3. Same way, there is number of resources are there R1, R2, R3, and the R1 having the number of dots, which is having the number of resource representing the number of resources are there. So there is P1 implies R1, means P1 allowed to access by R1. R1 implies P2, means R1 resource held by P2. P2 implies R3, means P2 requesting for accessing in R3, and R3 implies P3, means R3 resource is held by P3 process, means every resource is held by another process and requesting for another resource. So this is the condition of deadlock. In the same way, the resource allocation graph in the next diagram, resource allocation graph with the A deadlock. In this situation, we having P1, P2, P3 and P4 resources, and we have only 4 resources or 2 blocks R1 and R2. R2 resource requested by P1 and same R2 resource held by P4 resource, and R2 resource requesting by P3 and holded by P1. Same way, P1 requesting for R1 resource and holding that resource by P2 and P3. So every process requesting for another resource and holding a single resource, you can say every process requesting for a new resource and holding the previous resource, not releasing the existing resource, it may cause the deadlock condition. And you can see there is a loop is occurring, or you can see the cycle is occurring in the both diagram notation or graph notations of resource allocation. Now, dealing with deadlock situation, for prevention, disallow one of the 3 necessary conditions of deadlock occurrence. If we are able to do this, we can prevent our system to enter into the deadlock condition. Deadlock avoidance. Do not grant a resource request if this allocation might lead to deadlock. If any process requesting for such resource which may cause the error and which may cause the occurrence of deadlock, so do not allow that kind of resource to access or acquired for particular process. Now come to the next is deadlock detection and recovery. Grant resource request when possible, but periodically check for the presence of deadlock and then take action to recover from it. At the fixed period or after some duration of time, we have to check, or system have to check after allocation of resource if there is deadlock condition is occurred, or at the same time try to remove or resolve that problem, because this kind of problem may cause of waiting n number of processes for acquiring that particular resource. Next topic is deadlock prevention. Deadlock might be prevented by denying any one of the condition of deadlock. Like first is elimination of mutual exclusion condition. This condition is difficult to eliminate because some resource such as the tape drive and printer are inherently non-shareable. The next condition is elimination of hold and wait condition. Do not allow the processes to hold any resource and request and for wait another resource. Allow only that resource which is going to release existing resource and requesting for another resource. So there are two possibilities for the elimination of the second condition. The first alternative is that a process request be granted only the resource, be granted all the resource it needs at once prior to execution. The second alternative is to disallow a process from requesting resource whenever it has previously allocated resource. Now the next condition is elimination of no permission condition. The no permission condition can be elevated by forcing a process waiting for a resource that cannot immediately be allocated, relinquish all of its currently held resources so that other process may use them to finish their needs and that allocate to the another one. The next is elimination of circular wait condition. We have to eliminate this condition because this kind of condition possibly occur into the system. The circular wait can be denied by imposing a total ordering on all of the resource types and then forcing all processes to request the resource in order increasing or it may be decreasing order. The next topic is deadlock avoidance. This approach to the deadlock problem anticipates a deadlock before it actually occurs. This helps us prevent to our system from entering in a deadlock situation. A decision is made dynamically whether the current resource allocation request will, if granted, potentially lead to deadlock. If any allocation which is made by us or which is made by processor or which is made by operating system cause of deadlock, so do not allow that kind of allocation for any process. Require knowledge of future process request. If we have to allocate some resource, then try to know about the future request of another resources. The most famous deadlock avoidance algorithm from Dijkstra is the banker's algorithm. Two approaches to deadlock avoidance. Do not start a process if its demands might lead to deadlock. And the next is do not grant an incremental resource request to a process if this allocation might lead to deadlock. This is the banker's algorithm. The following are the features that are to be considered for avoidance of the deadlock as per the banker's algorithm. In this, each process declares maximum number of resources of each type that it may need. In this, banker says allow the number of resources which are required by a particular process, which may need and which is requested and which is required in future also. Next, keep the system in a safe state in which we can allocate resources to each process in some order and avoid deadlock. Define the ordering for allocation of resources to number of processes in that scenario. Next one is check for the safe state by finding a safe sequence. Which resource allocated to which process first? Like there is a number of processes like P1, P2 until and Pn, where resources that Pi needs can be satisfied by available resources plus resources held by Pj where j is less than I. Resource allocation graph algorithm uses claim edges to check for a safe state. If we are in a safe state, then we are going to allocate resources to number of processes. If any allocation may cause the deadlock state and may allow us to enter into the deadlock if we allocate that particular resource, then we are not going to allocate that particular resource at that time. The resource allocation state is now defined by the number of available and allocated resources and the maximum demand of the processes. Subsequently, the system can be in either of the following state. The first is safe state. In this state occurs when the system can allocate resource to each process in some order and avoid a deadlock, or it up to maximum allocation of resources which are required for a particular execution or for completion particular kind of task. This state will be characterized by a safe sequence. The next point is unsafe state. If the system did not follow the safe sequence of resource allocation method from the beginning, and it is now in a situation which may lead to a deadlock, then it is in an unsafe state. The next one is deadlock state. If the system has some circular wait condition existing for some processes, then it is in a deadlock state. These are the limitations of Banker's algorithm. The first one is it is time consuming to execute on the operation of every resource allocation and their releasing time. Second, if the claim information is not accurate, if P1 process require only R3 and R5 resource, but our expectation and their future need according to us R3, R5, R7, R9 and 7 and 9 resources are also required by another process, but we allocate it to previous one and that is not used by previous one, but they are required by the next process. So that kind of problem is occur. In the second situation, if the claim information is not accurate and system resource may be underutilized, which I told you and which we discussed in the previous example. Next is another difficulty can occur when a system is heavily loaded. When we allocate n number of resources to n number of processes, then situation is where the system is get overloaded and not handle the situations and computations related to allocation and related to release of the process and release the number of resources by the processes. Next is new processes arriving may cause a problem. Whenever a new process enter into the system, it always generates some problems, some issues related to allocation of resource, related to time, related to session which is required by that particular process for completion their task. Now the next is a resource becoming unavailable. Example, a tape drive breaking can result in an unsafe state. Deadlock detection. To detect a deadlock, we must go about in a recursive manner and simulate the most favored execution of each unblocked process. An unblocked process may acquire all the need resources and will execute that request. It will then release all the acquired resources and remain dormant thereafter. The next point is the now released resources may wake up some previously blocked processes. Continue the above steps as long as possible for prevention of deadlock or avoidance of deadlock. If any blocked processes remain, they are deadlocked. Now, this is the topic is deadlock recovery by process termination. In this approach, we terminate deadlocked processes in a systematic way, taking into account their priorities, their requests, their preferences. Process should be terminated based on some criterion policy. Some of the criteria may be as follows. Priority of a process. If a process has the higher priority and we are executing and the number of processes are in a queue which do not have the much higher priority, then their process have to terminate and need to terminate for execution of the higher priority process. Next is CPU time used and expected uses before completion. Next is number and type of resource being used. Can they be preempted easily? We can calculate how many resources and how much resources allocated to number of processes and number of resources are remaining for allocation and are remaining for further allocation. Number of processes needs to be terminated to preventing the system into or from entering into the deadlock situation or condition. Recovery by checkpointing and rollback. In this, about all deadlock processes, which are the causes and which are in a deadlock state. Next is backup each deadlocked process to some previously defined checkpoint and restart all processes. The first is originally deadlock may occur. Next point, successively about deadlock processes until deadlock no longer exists into the system. We are going to terminate only that kind of processes and that kind of tasks which are the causes of deadlock and which are acquiring that kind of resource which may cause of deadlock. So, by using this kind of steps, we can avoid or prevent our system from entering into the critical section problem, entering into the deadlock situation, successively preempt resources until deadlock no longer exists.